Hi, this is a rather short video about the strategy for vector line integrals. So, vector line integrals are the sort of problem of this sort of type, where you're doing an integral along a line of p dx plus q dy, or maybe plus an r dz in a 3D sort of world. There we have learnt, and I continue to learn, a variety of methods for doing it, so it depends where you're at. You might not have done them all. How do you pick, which method should you pick in a given problem? So here's some advice of what to do, how to break it down. So firstly, when you're looking at it, is look at if the curve is closed. So what does it mean if, basically, if the two endpoints for the curve end up meeting it together? So there is no start point. That means it's a loop of some description. So if it's a loop and it's in two dimensions, then I want to use Green's theorem, which is what I've written down here. I'm using it from the vector line integral to convert it into a double integral. Or you can, in a three-dimensional world, which would have a plus r dz, I'd use Stokes' theorem, which is essentially the same sort of idea. Probably the similar sort of theorem. And that basically means integrating along a loop just becomes a double integral. And if you differentiate these terms, which happens in both cases, that can end up simplifying what you're trying to do down. And a double integral, or in a surface integral in general, might be more straightforward to do. So that's the basic plan of attack. That's useful. Closed curve, Green's theorem, Stokes' theorem. So if the curve is not closed, then you can't use Green's theorem, so you have to use something else. So the next sort of big result, which is useful, is called the fundamental theorem of line integrals. So that's a good one to check for next to see if that's an option. That isn't so easy just to see just from looking at the curve, but essentially it is worthwhile checking if the vector field is conservative. Now in a 2D world, and you've got P and Q like I've written here, then you do the mixed partial derivatives, so just do the opposite partial derivatives to what in the order is written, and they should be the same, or the difference should be zero, same sort of way. And this term here crops up in the Green's theorem. So you want to check, and that should be zero for a conservative function. For 3D, similarly, the curl of f, which you may not understand yet, but this is called the curl of f, that has to be the zero vector in 3D for it to be conservative. And that crops up in Stokes' theorem correspondingly. So if you've got a conservative vector field, then you can work out the fundamental theorem of line integrals, which is great. That means you have to find the potential function. We're doing some various integrals, and once you've got it, then all you have to do is plug in the endpoints. And that's normally a pretty good way of doing it. So if you know it's conservative, that certainly saves some time. And that would be just something to check for. So just try these derivatives and see if it works. And if it doesn't, well, okay, that's not the way to do it then. But if it didn't work, you can see that these terms here can be useful other ways. So what happens if they both fail? Well, a backup option that works all the time is to parameterize the curve. So if you can parameterize the curve, then you do integration by substitution, which was the very first method we learned for vector line integrals. So that's always the backup. So they're the main methods: closed curve, Green's, check for conservative. If it is conservative, fundamental theorem of line integrals. Otherwise, parameterize. There are some advanced things which you can do or never try to do if you wish. I mean, those methods always work. Other advanced methods is to, if you've got a curve, is to try closing it. So adding a little bit to close off, and then use Green's theorem for the closed off part, and then work out the extra bit you joined on separately. Maybe using parameterization, for example. The purpose of that would be to make the new little bit you add on be an easier curve to parameterize and therefore solve for, where Green's theorem can be used for the closed part. So they're complicated. That's it works in some circumstances, and you need to think carefully about it. So that's not required, but in this sort of subject, but it gives you an idea that there is a variety of vector line integral methods. You do need to know the individual parts, and you need to have this idea of which one is appropriate when, etc. This is a little guide. So separately to this, I'll do some examples about how to actually use these results. Just before I do that though, I just want to talk a bit about the big sort of picture. So the conservative, if the function's conservative, then it really just depends upon the endpoints. Really nice to do. If it's not conservative, it gets a bit harder to do. What Green's theorem and Stokes' theorem, similar to that, is pretty much summing over the region that the interval contains is how different to a conservative function it is. So this little block here in Green's theorem really is the difference to a measure of how non-conservative it is. If it's completely conservative, this thing would collapse down to 0, which is a special case of conservative functions. So this is sort of this and the curl in the same sort of way. In one way I think of it is a measure of how non-conservative it is. Another way of thinking of it, so just a bit differently, so if you've got the vector field, consider it like a fluid, so this is how well the fluid flows, then both these quantities that you can see here also correspond to how much the vector field rotates. So this term is equal to 0, it suggests that there's no net rotation in the vector field. And the same thing with the curl, it's a measure of how much it rotates. And so this is a matter of rotation, so that this is summing up the whole rotation of the enclosed region. So if there's, on average, so if you add them all up, if you get no rotation at all, for example, so if you're adding up the rotation on the whole lot, will give you the total rotation just on the boundary, essentially what it's trying to say. So total rotation over the enclosed region surface is equal to the rotation on the boundary, called the circulation. And we'll see a bit more of that in Stokes' theorem. But in case these results are going, well, what's all that about? Funny looking symbols. That's a sort of conceptual understanding that might be helpful for these sort of things. But anyway, I hope that gives you some overview help, and we'll do the example separately, which of course you have to master.